So good morning students. So yesterday class we completed up to thermodynamic process. So today class we are going to start with the pressure, temperature, absolute pressure, gauge pressure, volume and work and heat transfers. So before going to today's class we will discuss about the yesterday's class with a small review of the 5 minutes. So yesterday we discussed about the thermodynamics. What is thermodynamics? Thermodynamic system, thermodynamic properties and state, path and process, quasi-static process, reversible process and thermodynamic cycle. So these are the topics yesterday we covered. So just can you tell what is an thermodynamics? So I will tell again once again what is an thermodynamics. So thermodynamics is nothing but the conversion of a heat energy into the mechanical energy is called as a thermodynamics. Thermo means heat, dynamics means motion. So uh, in examination what is thermodynamics means you can write like this: the science deals with the conversion of a heat energy into mechanical energy and the properties of the system is called an thermodynamics. And next coming to the thermodynamic system. So thermodynamic system is nothing but it consists of a system, boundary, surroundings and universe. So first we can tell what is a system. So a system is nothing but the region, that the space that contained matter and thus behavior is to be investigated is called a system. That is called a system. And next coming to the surroundings. So whatever the outside the system is called the surrounding. Outside the system is called the surrounding. And which is separate a line drawn, imaginary line drawn between the system and surrounding. So imaginary line which separates the system and the surrounding. Thermodynamic properties means the two types of thermodynamic properties. One is extensive properties, second one is an intensive properties. Extensive property is a dependent on the extensive property is which depends on the mass is called an extensive property. Example, mass, volume, internal energy, enthalpy, etc. are the examples of the extensive properties. Intensive properties means opposite to the extensive, which is independent on the mass of the system. Example, specific volume, pressure, temperature, etc. are the examples of the intensive properties. Like that, the state, path and process also is there. So state is nothing but the properties like a temperature, pressure, volume, etc. So change it from a one point to the another point is called as a state. So path means infinite number of states that occur when the system undergoes a particular process from a one state to the another state. Here there is an intermediate states from it going from a 1 to 2. So the line joining the series of states through which the system passes is going to the initial state to final state is called as a path. So if the initial state to final state, it represents in a one arrow, that is called as a path, and we will draw a line that is called as a process. So it goes from a 1 to 2 or 2 to 1. So that 1 to 2 or 2 to 1 is called as a process. So the term process means change in the state of the system, change in the state of a system from a one state to the another state, one state to the another state. So generally we investigated PV diagrams and TS diagrams. PV means pressure volume, TS means temperature and entropy diagrams. Next to the quasi-static process. Quasi-static process is nothing but the quasi means slow, static means equilibrium. It is slow in equilibrium. So if the process from 1 to 2 may be equilibrium, may not be equilibrium. So to reach the equilibrium, the intermediate steps means that one to another point. So slowly equilibrium states. So 1 to 1, 1 to 1, 1 to 1. So each intermediate states are in equilibrium states. So the system is in a equilibrium from a initial state to the final state. Initial to final state means so many intermediate states are also there. So that intermediate states are also should be in a equilibrium. The process is called a quasi-static process. If that intermediate points are not in equilibrium state, then the process is called a quasi-static. Then the process is not in a quasi-static process. Coming to the reversible process. So reversible process, the name itself indicates that the process that can be reversed so that the system restored to its initial state is called a reversible process. This is the reversible process. So what is the reversible process? Reversible process that can be reversed to the system restored to its initial state is called as a reversible process. Next one, thermodynamic cycle. So thermodynamic cycle is nothing but the sequence of a thermodynamic process that begins from starting to the ends at the same state and the returns to its initial state, and the system should be returned to the same initial state. If the thermodynamic process starts at A and ends at also the same point, ends at also same point. So 1 to 2, again 2 to 1. So it is in a closed loop. So 1 to 2. So state 1 to state 2 is a process is we are considering A, and 2 to 1 is a processing B. So 1 to 2 and 2 to 1. So A and B are the two process. So what is means the thermodynamic cycle means there's a sequence of the process A and B constitute a thermodynamic cycle means 1A 2B 1. This is the thermodynamic cycle. So in this class we discuss about the pressure, volume, temperature, absolute scale of temperature, standard conditions and energy forms. So pressure. So pressure is nothing but defined per unit area. Pressure is defined as nothing but the force per unit area. So pressures are exerted by gases, vapors and liquids also. So this how you calculate the pressure means by using the instruments like a manometer, barometer, etc. Low, or it's simply we can define as a pressure is a normal force to the unit area of the surface is called the pressure acting on the surface. Pressure acting on the surface. Pressure is often expressed in a units of a pascals or newtons per meter square, because the pressure is equal to force per unit area. Force is nothing but the newtons, area is equal to meter square. So other units of the pressure is also there, that is nothing but the atmosphere bar. So 1 bar is equal to 10 to the power of 5 Newton per meter square. 10 to the power of 5 Newton square. You can write it as a 10 square into 10 power 3. I am converting as a 10 power 3. I am writing as a 10 power 3 as a kilo. So it is nothing but the 100 kilo Newton per meter square. 1 Newton per meter square is nothing but the Pascal also. So 1 bar is equal to 10 to the power of 5 Newton per meter square or 100 kilo pascals. And like that, 1 atmospheric is equal to 760 mm of mercury, that is 1.01325 bar. So the simple examples of a pressure array. Uh, so we hold a knife to cut a piece of a fruit. If you hold the flat part of a knife against the fruit, it won't cut the surface, because the force is spread out the large area means low pressure, because the force is pressure is inversely proportional to area. Inversely large area means here the low pressure. if you turn if you turn the blade, so the cutting edge is pressed into the fruit, the same force is applied over the much smaller surface area, so the surface cuts easily. This is the best pressure. Gauge pressure is recorded by an instrument is called as a gauge pressure. So the pressure recorded by the instrument above the atmospheric pressure is called as a gauge pressure. So simple examples, for the gas cylinders we measure the pressure. So if you put a gauge means nothing but an instrument, we put an instrument upon the cylinder, it shows as the pressure is more than the atmospheric pressure. So that is called as a gauge pressure. That is called as a gauge pressure. Now coming to the vacuum pressure. So vacuum pressure is nothing but the it is a pressure is less than the atmospheric pressure is called as a vacuum pressure. It is the amount by which the pressure inside the container is less than the surrounding pressure. Surrounding. If this for the same gas cylinder, the readings which shows the less than the atmospheric pressure. So atmospheric pressure we are considering as a atmospheric pressure as a 760 mm of mercury or 1.1325 bar. If it is less than the standard atmospheric pressure, we can consider it as a vacuum pressure. If it is more than the standard atmospheric pressure, we consider as a gauge pressure. So gauge pressure. So vacuum pressure is always in the negative side of the atmospheric pressure. So this pressure vacuum pressure or the negative pressure. Next coming to the absolute pressure. So absolute pressure means we denoted it's a PABS. So the pressure measured above the absolute zero pressure. So whatever the pressure measured, we are taking as a one line as an absolute. We are drawing a graph taking as a pressure on a y-axis and absolute zero on a x-axis. Absolute zero on the x-axis. If you measure the pressure above the absolute zero pressure, is called an absolute pressure. This absolute pressure may is found to be a zero also. This situation occurs when there is a perfect vacuum. So absolute pressure is be obtained by using for following in two relations. So the pressure measured from this value is called an absolute zero is called an absolute. This is a relation between pressure and vacuum pressure. So pressure measured above the atmospheric pressure is called the gauge pressure. So after measuring the gauge pressure, we will get the absolute pressure by adding the atmospheric pressure plus gauge pressure. And pressure measured below the atmospheric pressure is called the vacuum pressure, and we'll get absolute pressure by measuring the absolute atmospheric pressure minus vacuum pressure is called an absolute pressure. So the two relations are the P absolute is equal to P atmospheric plus P gauge pressure. Again P absolute is equal to, in case of a vacuum, is P absolute is equal to P atmospheric minus P vacuum. So these are the relations between the gauge, vacuum and absolute. So clearly understand about the pressure. So is the pressure the two types: atmospheric pressure, gauge pressure, vacuum pressure and absolute pressure. So again I am discussing about the pressure. So pressure is nothing but the force per unit area. For the standard SI unit for the pressure is a Pascal. So 1 Pascal is equal to 1 Newton per meter square. 1 Newton per meter square, or you can write this as a kilopascal is also 10 power 3 Pascal. 10 power 3 Pascal. Pascal means nothing but Newton per meter square. And 1 megapascal. Mega means 10 power 6. So 10 power 6 Newton per meter square. 1 gigapascal is equal to 10 power 9 Newton per meter square. So these are used in doing problems. So again two additional units of pressure also used in the problems. One is a bar and then is atmosphere. So 1 bar is equal to 10 to the power of 5 Newton per meter square, or 1 atmosphere is equal to 760 mm of mercury. We can write it in terms of a bar as a 1.01325 bar. So these three things we have to remember. 1 Pascal is equal to 1 Newton per meter square. 1 bar is equal to 10 to the power of 5 Newton per meter square. 1 atmosphere is equal to 760 mm of mercury, that is equal to 1.01325 bar. So 1.01325 bar. Again coming to the atmospheric pressure. So atmospheric means nothing but the air pressure force per unit area. So whatever the force exerted by the atmosphere on a unit surface area is called the atmospheric pressure, and it is measured by a mercury barometer. So the standard atmospheric pressure we are taking as a 760 mm of mercury. Like this, a gauge pressure also is there. Gauge pressure is nothing but the we can record it the pressure by using an instrument that is in a gauge pressure, and that gauge pressure is above the atmospheric pressure is called as a gauge pressure. So whatever the pressure measured above the atmospheric pressure is called a gauge pressure, and the pressure measured below the atmospheric pressure is called as a vacuum pressure. So gauge pressure we are denoting the P suffix G, vacuum pressure we are denoting the P suffix V, P suffix V. So there is a relation between the absolute pressure, gauge pressure and the vacuum pressure. So P absolute is equal to atmospheric pressure plus gauge pressure, and P absolute is equal to P atmospheric minus P vacuum. So this figure shows the relationship between the gauge pressure, absolute pressure. And coming to the volume. So the volume, volume is a nothing but the space occupied by the substance. So generally we for the cube, what is the volume means is the length into breadth into height. So like this only is this volume is a space occupied by the substance. So volume is a depend upon the mass of the substance, and also volume is a extensive property. Volume is a extensive property. The basic unit of the volume is a meter cube or liter, meter cube or liter. The specific volume, so specific volume also we can define as a specific volume is nothing but the volume per unit mass of a substance. Volume per unit mass of a substance is called a specific volume. So specific volume is denoted by small v. Small v is equal to capital V by small m. Units are the meter cube per kg. Meter for the volume, units is a meter cube, mass it is a kg. So this is the volume. So 1 meter cube is equal to 10 to the power of 3 liters, or 1 liter is equal to 10 to the power of minus 3 meter cube. So again I am telling about the volume. So volume is a substance, so which is occupied the space by the system. So volume is the space occupied by the substance, and it is dependent upon the mass of the substance also. So extensive property, volume is an extensive property also, because extensive property is nothing but it is depend upon the mass. So basic unit of the volume is a meter cube, and it is expressed in liters. So the specific volume also we can define as the specific volume is nothing but the volume per unit mass. So volume per unit mass of the substance is called the specific volume. So specific volume is denoted with the small v, small v. So small v is equal to volume divided by mass. So units for the SI units is a volume. Volume means meter cube, mass means kg. So meter cube divided by kg. So 1 meter cube is equal to 10 to the power of 3 liters, or 1 liter is equal to 10 to the power of minus 3 meter cube. Density. So density is nothing but the reciprocal of the specific volume. So density we are denoting with the rho. Rho is equal to 1 divided by specific volume. 1 divided by specific volume. Specific volume means volume divided by mass. Volume divided by mass. Here it is volume is equal to volume divided by mass. So density is nothing but the reciprocal of specific volume, means density is equal to mass by volume. So SI unit is equal to kg per meter cube, where m is equal to mass, capital V is equal to volume, small specific volume. So this is about the density. So density is nothing but the reciprocal of the specific volume. Next, coming to the temperature. So temperature is nothing but the indication of a hotness or the coldness, and therefore it is the measure of a intensity of the heat. So measure of the intensity of the heat. It indicates that the thermal state of a body to transfer the heat energy, So in the metric system, the temperatures are usually measured in degrees absolute scale of temperature. So the like absolute pressure, there is an absolute scale of a temperature is also there. So general temperature we are denoted with a small t. Absolute scale of temperature here we are denoting with a capital T. And for the temperature, the units are the degree centigrade, and for the absolute scale of temperature, the units are the Kelvin. We are denoted with a Kelvin, and we are write with a capital K. So the temperature scale calibrated above absolute zero is called the absolute scale of temperature, or Kelvin scale of a temperature. So whatever the temperature measured above the absolute zero is called an absolute temperature. So absolute the measure about the absolute zero is called the absolute temperature. So the basic unit of the absolute temperature is Kelvin. So if, how will you convert the temperature to the absolute scale? Means we are taking as a 273. So if it is a 27 degrees centigrade, so what is the absolute scale of temperature? Means capital T is equal to 273 plus 27 is equal to 300 Kelvin. 300 Kelvin is an absolute scale of temperature. So the units of a Celsius and Kelvin temperature intervals are identical, so that cap dt means uh, temperature, capital T is denoted for the absolute scale and the t is denoted for the small t is denoted for the temperature. Capital T is denoted for the absolute scale of temperature. Next, standard conditions. Some standard conditions for the temperatures and the pressure as well. We call it the standard temperatures and pressure, normal temperature and pressure. We call it the STP and NTP. Atmospheric conditions are usually stated in the following terms. One is STP and another one is NTP. For the problem, while solving the problems, so they will give at STP conditions. So calculate whatever they will give, we have to calculate. So for that, at STP conditions, we have to take this temperature is equal to 15 degrees centigrade and the pressure is equal to 760 mm of mercury. At NTP conditions, the temperature capital T is equal to 0 degrees centigrade and pressure is equal to 760 mm of mercury. That is a 101.3 kilonewton per meter square. Kilonewton. To the next topic, here is an important topic in this, the energy forms in the area of the thermodynamics. So energy forms. So most of the applications in the area of the in the area of the thermodynamics, the mass is considered constant while analyzing the energy in a transaction. So heat and work, here the energy forms are the heat and work are two most fundamental energy forms and essential to understand the thermodynamics. So heat and work are the two most fundamental forms of energy in the thermodynamics. For the most of the applications in the area of thermodynamics, mass is considered as a constant while analyzing the energy in transition. So next, heat and work. The first one is the heat energy. So heat energy is the form of energy which crosses the system boundary due to temperature difference between the system and surroundings. So in the thermodynamic system, while considering there's a closed system, open system and the isolated system, here the both the we are considering the two parameters, mass and the heat. So in that open system, in that first one closed system, only heat transfer is given, and we consider a flask. In that flask some liquid we are pouring and we seal the flask with a cap, and we are giving heat, we are giving heat, and the mass transfer is not going out, the mass is a constant. We are giving heat, heat is going out to the system, out from the system. Like that, heat is defined as energy crossing the system boundary because of a temperature difference between the system and surrounding. So heat is giving to the system and leaving from the system into the system, outside the system to the surrounding. This is the difference between the system and temperature difference between the system and the surroundings. So heat is not stored or processed by the system. Heat contained by the system can only be identified and felt only when it crosses the system boundary. So the amount of heat energy transferred from when a system changes from state 1 to state 1 and depends on the path followed by it. Path, heat is a path equation and heat in a inexact differential. So heat transfer to or from a system undergoing a process from a state 1 to state 2 can be written as a q is equal to integral of a differential q. So state 1 to state 2 following the path. So heat flow is represented by a q, and is a function of the process in which the energy is a transferred, that in which energy is a transfer, that is it is a path function. So in mathematically term it is called as a inexact differential equation. So heat transfer to or a from a system undergoing a process from a integral 1 to 2. Integral 1 to 2 represents as a undergoing a process from a state 1 to state 2. So state 1 to state 2 dq. So where q12 represents the amount of the heat transfer when the system changes from a state 1 to state 2. So units of the heat are the joules. Sign convention of the heat transfer. So this is the main important one. So heat energy flowing into the system. So we are giving the heat into the system from the surrounding. We are giving the heat to the system from the where we are giving heat from the surrounding. So we take it as a positive, and heat energy flowing from the system to the surrounding is a taken as a negative. So heat is coming out from the system to the surrounding is a W12 is equal to integral 1 to 2. So dW integral. So like heat Q12 is equal to integral 1 to 2 is equal to dQ. Here also work we are writing as a W1 to 2 is equal to integral 1 to dou W, where the quantity W12 represents the amount of the work done by the system or on the system when it changes from a state 1 to. So sign conventions of the work transfer. Here is a sign convention is just opposite to the work transfer, just opposite to the work transfer, opposite to the heat transfer. So work is done by the system on the surroundings is taken as a positive. Work is done on the system by the surrounding is taken as a negative. So units of the work are the joules or kilojoule. 1 joule is equal to 1 Newton per meter. So here the work is nothing but the force into displacement. So force is equal to newtons and displacement or the distance is equal to Newton. So units are the 1 Newton per meter or 1 joule. Convention of the work transfer. System, boundary, surroundings. Work is positive, negative, and work coming out, going to the system is negative, coming out from the system is here positive. Here is the sign convention. So whereas the comparison of the heat and work, comparison of heat and work. Heat and work are the two different forms of a transient energy. Heat is transferred because of a temperature difference between the system and surrounding, whereas the work is transferred because of a property difference other than the temperature. So heat and work are both in transient phenomenon. Transient phenomenon. System never possesses heat or work, but either or both the cross system boundaries when the system undergoes a change of a state. Here I am telling once again, heat and work are two different forms of transient energies. Heat energy transfer across the boundary due to temperature difference between the system and surrounding. So heat transfers across the boundary. So it transfers the heat due to because of a temperature difference between the system and surrounding. So whereas in coming to the work energy, so transfer of work energy results from the action of a force on the boundary, because it is work is equal to force into distance. That's why the transfer of a work energy results from the action of force. Is the force is an important here, the action of force on the boundary, action of force on the boundary. Neither heat or the work can exist or as a stored energies, that is they are energies that they are not the energies possessed by the system or body. The amount of heat and the work transfer depends on the only process. The amount of heat and work transfer depends upon the process means 1 to 2, and depends upon the path between the two states. Between the two states means 1 to 2, state 1 state 2 represents, and followed by the 1 to 2 process, it represents the path. So the amount of the heat and the work transfer depends on the process, so the area under the PV diagram or the TS diagram represents the work transfer and the heat transfer. So the amount of the heat transfer is obtained heat transferred is obtained by using the equation Q is equal to some integral 1 to 2 TdS. TdS means temperature change. TdS means temperature change, and W is equal to integral 1 to 2 PdV. PdV means pressure into volume. So TdS means is a temperature entropy, PdV means pressure volume. This is the work and the heat transfer. So in this class we learn about the pressure, volume, temperature, and the absolute scale of temperature, and the standard conditions and the energy forms. So energy forms are the important for the calculation of a problems and for the calculations of the problem. In the next class we discuss about the specific heat, internal energy, enthalpy, flow work, and some problems. So thank you students, thank you very much.